what we're going to do is kind of get started talking about flow simulation. Now, flow simulation is just one of many analysis programs that SolidWorks offers in the SolidWorks suite of programs. And flow simulation happens to be one of the more powerful ones. It's going to handle pretty much anything involving fluid flow. Now, there are some specific limitations, so if you have an application in mind that you're wanting to use this for, feel free to reach out to one of our application engineers. You can reach out to me directly. I'll post my contact information again at the end of the presentation, and we will be recording this so you can watch this again later if you need to. But flow simulation is going to take into account anything fluid, liquid, pressures, pressure distribution, flow, pressure loss, forces, some pretty powerful functionality. And what I've got here is just a really simple analysis of a truck. And you can see that it's going down the road at a specific speed. I think it looks like it's 70 miles an hour. And we're able to take a look at the pressure distribution across the truck, which is going to take us and help us understand what kind of drag forces we're going to expect. We can also see around the truck itself where you might see high or low pressure points. So this can help us with design of certain aspects of the truck, maybe some of the accessories and things like that, to try to make sure we get an optimum design. We can really do some amazing work in understanding what's going on, but to get started, to kind of give you an idea of how the software works, I'd like to take you through a really simple example. All right, I'm going to actually just run a brand new model and set up a study and take a look at the results. And it's going to be a really simple one, but it'll give you a really good idea of how the software works. And then we're going to kind of play around and look at some of the more advanced capabilities, look at some really cool examples. Like I said, I'll take some requests if you have them. So the first thing I want to do is look at this example that we're going to run through, and it's a piston valve. And so I'm going to do a section view just so you can take a look at the inside of it. Here we go. And everything over on the left, most of this stuff is not going to be involved in the analysis. What we do have, though, is on the far right, right here, this is the inlet for this piston valve. And what we're going to see is water coming in, very high pressure water coming in and pushing this valve, this piston, push it down. And the pressure of the incoming water flow is going to push it against the spring. I haven't modeled the spring. I left it out just for simplicity. But as it pushes that spring down, it will move the piston back and open that up even further. And so what we want to understand is what the fluid flow is going to look like, what pressure drop we're going to see, what the force is going to be on that piston, which would then determine how far down that spring is going to compress. Really simple setup, not much to it, but it does a nice job of illustrating how flow simulation works. And so it's kind of an easy as 1, 2, 3 kind of a situation. You start out by telling it what you know or what's going on, and you tell it what you know, and then you tell it what you want to know. So I'm going to start out with this wizard. And this wizard, normally I would stay away from wizards or little guides or things like that are kind of walk me through with a dialogue. In this case, the wizard inside flow simulation really is like a checklist. These are all the things that you need to address. So I'm going to say this is some water. This is my project name. It's going to be water. And then units I feel comfortable in. Now I'm going to be SI units. I want to do some metric units. But not all the units are across the board metric, right? Very often, maybe instead of pascals, you want megas. In this case, I'm going to use the units as bars. For velocity, instead of meters per second, maybe I want miles per hour. Maybe I have kind of a weird mixture of units. That's no problem, especially certain applications that units become kind of a mixed bag. If you have a very specific application where you're always using the same set of units, you can actually create your own unit system. I'm going to call this my unit system. And anytime I need to create a new system or a new project from this point forward, it's always going to remember my favorite or my preferred units. Now we can do an internal or an external study. This is going to be an internal study. That truck, for instance, was an external study. If you do external, you can also do internal. So you can do both, things like radiators where you have hot liquid and cool air coming across. Those can be done simultaneously. And none of this is really going to be important. We're not doing any heat conduction. We're not worried about radiation. It's not a time-dependent solution. But you'll notice just by looking through here and breezing through the list, we can figure out what we can turn on to make sure we get an accurate solution. Let's find out what we can turn off in order to get a fast, efficient solution. For the fluids, I'm going to add water and just use water across the board. Now, with water, I can do things like cavitation. I could also mix stuff with the water. So if the water was coming in at a certain concentration and I wanted to understand how that mixture was going to happen, that's definitely possible. As I continue on, most everything else is going to be set as default, things like ambient temperature and pressure. But once I'm done answering all those questions, Flow Simulation is going to create this domain. And it's recognized the internal volume of this valve, and it's telling me that it's going to run the solution in this area. Now, I don't actually need to know what the flow is back here where this spring is. That's an isolated area. We're not going to have any analysis done back there. And so I have the opportunity to just pull the domain up and make it smaller so that it fits exactly of my concern. So this cubic area or box area, that's where my analysis is all going to occur. And I don't have to worry about meshing or controlling or worrying about any of these other items. Go ahead and hide that domain so I can get it out of the way. And now we're going to start telling the software what we know. Now, what we usually will know is things like pressure drop or flow rate or velocity. Any number of different things you might know or you might think you know. Pick one, whatever you feel the most comfortable with, and tell that to the program. That's going to be what our analysis conditions are. So the most common thing you'll use is a boundary condition. Boundary conditions just say, I know the status of whatever is outside the system. So when I say I want to do a boundary condition, I know that this piston valve is inserted into a tank, and that tank has a pressure, because I have a pressure gauge on the tank as a pressure of 2 bar. So I'm going to click on this face to set that pressure. Now, it might look a little weird. I have this little disc just sitting at the end of this valve. You have to set a stop for your domain somewhere, right? I don't want to analyze the world. I just want to analyze what's going on in here. And beyond this point, it's not important. So SolidWorks Flow Simulation, in order to set up boundaries, I just put lids on everything. And there's an automatic lid tool, but really just anything you have, just smash it on the front, and where it blocks that opening, that's going to be where the fluid is defined. So I don't have to model the fluid boundary. I simply have to cap off the areas of interest, and then those caps become my boundaries. So that's my first definition, which is the pressure opening here at 2 bar. I have another boundary condition at all these outlets. Now, if you can kind of see these outlets, there's 4 spherical cuts, or cylindrical cuts, 4 holes all the way around the outside of this. And there's a sleeve that's been slid down over it to define what's, that closed area. Because once it hits that opening and hits that sleeve, it's going to eject out of this valve, and I'm not concerned where it goes from there. So this one is also going to be a pressure, and this one's going to be 1 bar. So pretty simple, 2 bar to 1 bar. We're just going to have water coming in, and it's going to go from high pressure to low pressure. Very simple. Now, if there were other things going on in here, heating elements, fans, if there were regions that were spinning, if there was just about any other condition that was important, or any other openings or walls or anything like that that I needed to specify, I would do that at this time. But that's it. That's all I need to know. That's all I do know, actually. If you know more, you can add more. And now comes the part where I tell it what I want to know. Now, in this scenario, what I want to know is a few things. I want to know, for instance, the flow rate. So I'm going to create a goal. Now, these goals can be measured in different areas, but you kind of think of it as a measurement, a gauge, right? You can look at the gauge and keep an eye on it and find out when your gas tank is full in your car, for instance. Well, here, I'm going to tell the software that I want them to look at the average static pressure at this inlet to make sure that everything's accurate. If the average static pressure has been met, I'm feeling very comfortable that my solution is done. My tank is full. My answer is correct. But I also want to take a look at the mass flow rate. So those two things are my parameters of interest. As long as those two answers are correct, then I'm going to be good to go. And by specifying them as goals, not only am I going to be able to view them and keep track of them as time goes on during the solution, but it's also going to allow the solver to know what's important, and it's going to actually optimize the solution. So the software solver is going to speed up or slow down the solution to make sure my answers are correct. Makes it really handy. And I'm ready to go. The only other thing I might want, and this is the last thing that I'm concerned about, just it's kind of a nice thing to be able to do, I want to know on this piston how much force there is. Because the water's coming in and hitting that piston and being pushed around, I know there's going to be some force, and that force is going to be in the X direction. I want to know the value of that force, because I'm going to have to come in here and size the spring at a later point. So by knowing the size of the spring or knowing the force, I can analyze that pretty quickly. I'll go ahead and run this study. Now I can take into account multiple CPUs, so if you have a highly multi-core processor, no problem, we can do it. You can even run this at another computer using a remote solver. But it's pretty straightforward. It's just going to go ahead and save my model and mesh it and start calculating it. Now there's a few things that you can do as you're solving. So in the middle of the solution, you can go take a look at the pressure distribution. And you can see here that as my solution continues and progresses, it's making converged, or it's converging to a solution that shows an accurate distribution of the pressures and the forces. So here's my pressure values. I can also switch that if I want to show, for instance, the velocity, so I can see where that fluid is moving. Once the solution is done, it automatically brings me right back to SolidWorks so that I can take a look at the results. Here's an example of a pressure distribution cut plot. And you can kind of see that the pressure is highest right here at the tip of this piston, but also as it comes around and swirls around to get to the bottom. Maybe change that a few different ways. I might want to show, instead of pressure, maybe show the velocity. I might even want to show streamlines. And streamlines are these lines that are rendered by the graphics card, so they will zoom in and zoom out as I go, so I can get more detail if I look closer, and the detail goes away as I get further away. But it really helps me to understand where the fluid's going. You can see it's coming down and around. We're seeing a little bit of swirling in the middle, and then as it bends and kicks over here to the outside, there's some swirling going on at this point as well. A few other things I can do to visualize this information. I can do things like surface plots. I want to take a look at the distribution of the pressure on this piston. So I'm just going to grab all the faces of that piston and take a look at the pressure on that face. And that pressure is going to be what's participating in the pushing of that spring. So as the spring pushes down, we're going to, or as the spring pushes up, the fluid's going to be simultaneously pushing down to maintain the position of this piston. As far as where the actual flow is going, I can do things like a flow trajectory. A flow trajectory allows me to say, you know, let me see where all this fluid is going. And you can kind of see it shows lines that describe where that fluid is going. Let me add a few more lines here so I can kind of get a little bit more understanding of where everything's going and what's going on. So looking at it from the top, I can kind of see where the fluid is going. If it comes in between the two holes, it swirls a few more times than it would if it was near a hole out of the gate. The last thing I'll show is that force plot and the mass flow rate plot. And what I want to know is how much force is there. It looks like it's 8.3 newtons, so we have a pretty good understanding of the force, so we can size our spring. And we also know a lot about the mass flow rate, 0.15 kilograms per second. If I need to change those units to make them more comfortable, I can definitely do that. But flow simulation is not terribly difficult or complicated to run. These are the kinds of results you can get, understand what changes in geometry would do to the final outcome. Let's take a look at a few other examples or a few other applications that you might have that you might use this for. So here is a strainer. This strainer has fluid coming in on the left-hand side, and it goes through this mesh, and as that strainer strains out any particles and anything like that, it's going to go through and finish out to the other side. So I've specified we have a flow rate on the inlet coming in, and then we know kind of what the pressure is going out, and we have a few goals as far as the efficiency of this valve and the pressure drop coefficient. But basically, once I run this and load these results, it's a very similar setup to the last one, we'll see the distribution of the velocity. And I'll even kind of change the scale a little bit here so you can see where the velocity is. I can also take that cut plot and pull it in and out through the domain to take a look and see and investigate what the flow is like throughout that domain. I can also do my flow trajectories here. And I'm going to go ahead and play this one. Hopefully this comes across okay on the webinar. But if you take a look at it, what it's doing is it's coming in and hitting the front of that strainer. And it's a fairly open strainer, so it's pretty much just deflecting it downward and going through those first few holes. It's impinging on this face right here, so we're getting some high pressures in that zone. And then it either separates and goes out the outlet, or it sort of slowly circles and cycles around the outside of this, this strainer. So by understanding the fluid flow, the directionality, we know where particles are apt to start collecting. We know where it might self-clean or where we might get some recirculation. We know what pressure drops are going to see. We can also take this information and take a look at the pressure on the walls. So here is the pressure distribution on the walls, the inside walls of this system. This can also be used to calculate things like erosion. So if they've got particles coming in here, which is pretty likely considering we're running a strainer, and those particles hit that wall at a high speed and there's sand in there, we can start to calculate or compare design changes to see what effect that's going to have on our erosion rates. But this pressure can also be used for structural. So I'm going to take this study and I'm going to go turn on simulation. Now I mentioned up at the front, flow simulation is a fluid tool, helps us to understand the distribution and the movement of fluids, gases, liquids, etc. That's just one example of a software tool, the other one being SolidWorks Simulation, which is a static study. And it's going to be kind of a structural analysis. And I actually have one built already. And all I do is tell it, okay, I know what the pressure distribution is based on this fluid flow flow simulation study. Go ahead and take that and convert that into a structural load. And for good measure, I went ahead and applied some nozzle loads as well, because I'm probably going to see some additional loading from the rest of the system being applied to this housing. We take a look at these results. Go ahead and hide my cut plot. There we go. You'll see that inside here, the stress on the overall housing is really minimal. Everything's all blue. Blue means very low stress, and we're not really concerned with failure in this strainer. But because of that high flow rate, we did actually see some high stress in this strainer. And so we can understand and take a look at what value we have on the stress in that strainer, and we can start to size and maybe try to understand the life expectancy of that strainer given things like the erosion rate, the stresses. We can run a fatigue study from this result to understand, based on pressure spikes or pressure loading in the system, what kind of a lifetime we can expect, or life expectancy, on this filter on this screen. So this is another example of a closed system with a defined inlet and outlet going internal. Everything's very controlled in this scenario, and we can take those these decisions. Take a look at the distribution of heat in here. And get some solid results. So here's the temperature distribution in the air around this. So you can see in the main part of this, right in front of the doors, the air is coming in. We're getting nice, cool air. But then we're getting areas in the back that are stagnant. We're not getting enough air to go back there. And in fact, what we discovered on situations like this, on installations like this, we are able to predict where we're going to have issues with fluid flow and actually predict failure in the final product. Another look at that from the side. Here we can see with these flow lines, you'll see the air is kind of coming in, floating around at the inlet, not doing a whole lot. And we're not seeing very much recirculation up at the top, so we're just heating this hot air is just getting trapped up here in the top. And then as it comes around, it actually goes up through this channel. These are some heat sinks, and out the top through a blower. Another way to visualize that is with particles. I'm going to play this, and if we take a look, you'll see that the airflow is coming in very slowly, and it's cold. You see that blue color. And then as it goes down, we're starting to see it come up and around and through this channel of heat sink. But we're seeing some slow recirculation down here at the bottom. That slow recirculation is not very efficiently removing that heat. And so anything that's down there that's generating a burst of heat, and there actually isn't anything hot down there, it just happens to be stagnant air, we're going to see some problems evacuating that. And by using this tool, we're able to make minor changes, things like baffles, things like redirecting that air, and making small design decisions that actually create a more efficient design. It ends up not really being or requiring all that much effort to be able to make your design tremendously better in some situations. Another thing is with these is as you're looking at this, you'll start to get a feeling for these results. You'll look at the results, you'll look at the airflow, and it starts to make a whole lot more sense. Very much like engineers can look at a structure and start to understand, okay, well, I bet that's going to break there, or I bet that's the weak member, or that's going to be in torsion, and I'm going to have to keep track of that. Very similarly, you can start to get that gut feeling and that knack for understanding the thermal distribution, and you can start to address problems before they ever even start. I'm going to take it another one. This one's actually an example that I did recently. This one's near and dear to my heart. This is some beer, and this beer I actually have a freezer full of beer. And this is going to be an upcoming webinar that we're going to be doing, or actually not a webinar, it's going to be a YouTube video of creating and analyzing a system of cooling down beer quickly. My first guess, or my first thought, was to just go ahead and throw the beer in the freezer and wait for it to cool down. And so that's what I did, and you can start to see the distribution of the heat inside here. Because flow simulation is taking into account the fluid flow, it very accurately accounts for convection. And so for thermal situations, it's very powerful for being able to take into account and work on thermal systems. All right, so this one happens to be just a temperature plot at 2 hours. So at the end of 2 hours, you can see everything got pretty cold. But if I was to change to maybe a different time, and this is a time-dependent study, so I can look at any time step along the way. So let's say 45 minutes. How cold was it at 45 minutes? I'm itching to get some beer, and it's been 45 minutes since I threw it in the freezer. What kind of temperature can I expect? And in this situation, looks like we're getting around the 50-degree mark. And I can come in and actually start probing this to actually pull data off of it. Now, this is the kind of information that you would be able to do through a test, but it's very easy inside of flow simulation to run multiple scenarios, to ask a lot of what-if questions, to run multiple scenarios and grab data and graph that data. So for instance, let's see if I wanted to do a goal plot for the temperature, the maximum temperature in the fluid of one of these cans. I can actually look at that versus time and export that to Excel, and it creates a graph. So if you've ever seen graphs for like fan curves, performance graphs for systems or anything like that, I can actually take and look at the distribution of the temperature in that can versus time. So it gets colder. That's my genius conclusion of the day. So far, does anybody have any questions or requests regarding flow simulation? I've kind of gone through several different examples, but when you're dealing with flow simulation, the power is actually pretty amazing. The real benefit of using flow simulation is that it's not an extraordinarily complicated program to pick up and learn and use. In the case of this beer freezer, I simply told it what temperature the beer started out as, what temperature the freezer was in, and then I just threw all the pieces in the freezer and let it rip. We will be doing this, or I will be posting this on the MLC CAD YouTube channel. And so we're going to be doing some of that and talking about accuracy with respect to computer simulations. So I hope you guys have enjoyed what we've talked about today. I've just kind of gone through some random examples of flow simulation and being able to kind of quickly analyze systems and analyze and understand what's going on inside of these various components. So I'll open up one more and kind of just take a much closer look at how the beer cools down, just in case, you know, I always think it's really awesome being able to watch the fluid flow in the convection inside that beer. Because what happens is you actually see the beer is getting cold on the outside, which is causing the beer along the sidewall of the bottle to get colder. And that cold beer, dense, starts to drop along the bottom, which induces a convection. And so you get a current of what is relatively hot beer shooting up through the middle of the bottle. As it cools down, it drops down the sides. The bottle shape actually creates some vortices in here. So things like the red stripe bottle or any other kind of bottle, you'll be able to take a look at that and see how that benefits or hurts your heat transfer rate. I hope you guys enjoyed it. I've had a lot of fun. If you have questions, feel free to hang around, and I will answer those questions. I'm even going to take some requests if anybody has them. Be able to run through just about anything you would want to look at in SolidWorks Flow Simulation. Again, my name is Marcus Brown. Thank you for taking the time out of your day